In the given circuit, a steady current, a steady current, um, the potential drop across the capacitor must be. So, this is a circuit with resistors and capacitors. Steady current, meaning once a circuit is connected, the current will pass through the capacitor, but once capacitor is fully charged, then the capacitor will act as an open circuit. The capacitor initially allows the charges to flow through the capacitor. Once it's fully charged, there won't be any current flow through the capacitor. Or another way you learn in alternating current chapter, the capacitive reactance for a DC circuit is infinity. So it blocks DC. It conducts through AC. If you're learning alternating current and approaching this chapter, then it'll be fine. Otherwise, you have to keep in mind the capacitor. It's actually open circuit. There's no connection between the plate 1 and plate 2. So no current will flow through the capacitor. But once you switch on the circuit, the capacitor will get charged to both sides. That time there'll be a flow of current during the charging. Once it's fully charged, since this is an open circuit, the DC circuit, the capacitor don't conduct current. It will have voltage, it will have charge energy stored inside, but it won't conduct once it's fully charged. That means this branch you can imagine to be absent in steady state. This particular branch, central branch, can be imagined to be absent in the steady state. You deal with current, you can neglect this branch. But energy, voltage, charge, and all, you have to take the capacitor into account. This circuit is like without current flowing through the central branch. The point is steady state capacitor in DC circuit act as open circuit. The current through the capacitor branch can be neglected. Now the current only flow through the outer branch. The current direction is given here. So this current will flow to complete its path. We'll mark the current as I. You can find the current using the Kirchhoffs rules. Rule number 2. When you apply rule number 2, the rule is total potential difference over a closed loop equal to 0, which include the cell and the resistor. When you apply the Kirchhoffs rules, there are signs for potential difference. One convention we do, we mark the potential difference across the resistor as positive where the current is entering and negative current where leaving from the device. The concept is current flow from higher potential to lower potential in a resistor. The same here, the current is flowing from right to left. So current flow from positive to negative potential. For a cell, the positive and negative polarities are already marked. The longer one is plus and shorter one is minus. Here also, this is plus and this is minus. So when you apply the rule, you can start from A, B, C, D, E, F. So in this loop, we start from AB. The potential difference is 2 volt. 2 volt. You take the sign of the terminal where you exit the device. As you go from A to B, the sign you exit from the device is plus. So the potential difference is plus 2. We're just writing 2. But the next one, when you leave the resistor, you're leaving from the negative terminal, so the potential difference is negative. This is one of the sign conventions used. There may be opposite sign conventions with different directions. Now this potential difference is for a resistor I into R. I is I into 2R. So totally 2 times IR. This current will reach B and go to resistor R. Here also you are exiting the resistor from the selected path from negative terminal. So current is I, resistance is R. When you pass to the cell along the selected path, selecting the path A, B, C, D, E, F. Through this path, you exit the cell from negative terminal, so minus V. The total potential difference is U. Now 2V. 2V minus V is V. Is equal to 2IR, IR, 3IR, 3IR. So V by 3R will be the current passing through the circuit. So this is the current passing through the circuit. Now, if you want to find the potential difference of the capacitor, you must take a loop including the capacitor. So A, B, C, then F, A. D part we don't want. So A, B, C, F, A. Here also the current is going this particular way till here, but no current through the capacitor branch. So this resistor current is going from its positive terminal to negative terminal I. So A to B 2 volt. You're leaving from the positive terminal of the cell, so plus 2 volt. Here you're leaving from the negative terminal, so minus I into 2R. And here capacitor. This capacitor is connected to 2 volt here, positive, and 1 volt, just V volt here. 2 volt is greater, so this end will be plus, that side is plus, this side is minus. So you can just take as capacitor voltage as VC. As you exit from the negative terminal, minus VC. You exit from the cell from minus terminal, so minus V equal to 0. So 2V minus V is V minus I. I already we calculated as V by 3R. V by 3R into 2R. V already subtracted 2V minus V equal to voltage of the capacitor to the right side. Now you simplify this. V minus RR get cancelled. 2V by 3. So LCM by 3 minus 2, just V by 3. So voltage of the capacitor is V by 3. Using this, even you can find the charge stored in the capacitor, not asked here, but it's asked in another question. So Q equal to C times V, just C times V by 3. Energy stored in the capacitor is half C V square. So C by 2, V square will be V by 3 square, 9. So it will be C V square by 18. This can be an option to find the voltage, charge, and energy stored in the capacitor in steady state.